In the previous video, we talked about potential energy, and maybe I'll review it a little bit. So, you have a system of objects, right? And if the force acting within the system is a gravitational force, an electric force, or a spring force, then you can assign values called potential energy depending on the orientation of the parts of the system. That's basically what I told you in the previous video. And how you assign values depends on the amount of work you do in changing that system from one state to another, and that there is a difference in their states. The difference is the change in orientation of the parts of the system. But I mentioned work. The amount of work that you put into the system will result in the change in potential energy of the system. Work is a physics concept, and I'm sure you talked about that last year with your physics teacher, but I want to review it right now. A force does work on an object if it causes the object to move. It's the very basic definition of work. In fact, there is a mnemonic. I like to call it a mnemonic. Work equals force times distance. It's a mnemonic because it's not exactly correct. It's incomplete. There's more to work than just force times distance. And this is the formula for work. FD cosine phi. So that's the formula for work. Um, F is the magnitude of the force, like the value of the force, not taking into consideration the direction of the force, just the magnitude. So it's positive. D is the magnitude of the displacement. Again, it's a positive number because it's only taking into account the value of the displacement. So how far that you move the object while applying the force. And phi is the short angle between the force and the displacement vector. I want to elaborate that a little bit. So if you have an object and you're moving the object to the right, your displacement vector is to the right. And if you're pushing actually in this manner while moving the object to the right, because that's possible. That's what you do when you go to the shopping mall and then you push on the push cart. If you're a tall person, it's not like you're pushing parallel to the floor, you're pushing downwards. So here you're pushing southeast direction, and but that's causing the box to move to the right. So what's the phi here? The phi is the short angle between the force and displacement. How do you determine the force and displacement short angle? Well, you connect the two forces by the tail. So what I mean is right here. You redraw the two vectors, you redraw D, and it's still pointing to the east. And starting from the tail of D, you draw F, because you have to connect the tails, right? And the short angle, there are two angles here, the long angle and the short angle. The shortest angle would be phi. That's how you do the figure out the short angle. Short angle is 0 if F and D are in the same direction. And if they are in opposite direction, F is, for example, F is to the left and the D is to the right, you still have to connect them by the tails. The angle is 180 degrees. And if you try to plug that in, you'll find that cosine 180 is -1. So you get negative work. Let's have this example. A constant force F is applied to a box. F equals 10 newtons, 30 degrees. The box is displaced 10 meters. Ease. I should just have mentioned that. Yeah, so that's how you do it. The displacement is to the right. And our short angle is 30 degrees because although that is the angle for the force, 30 degrees, that is the angle for the force, but that also happens to be the angle phi, or the short angle, because the displacement is to the right. And when you redraw the arrows once more, you'll find that that 30 degrees sits here, and that location also happens to be the short angle between F and D. We get 86.6 joules. Yeah. Can we assign a potential energy for this? Like, can we also say now that the box has a potential energy of 86.6 joules? Because, the orientation is different. The previous snapshot, it's right here, and the next snapshot in time is already somewhere to the right. So, can we say that the box now has a potential energy of 86.6? No, we can't, because this force is not an electric force, nor is it a gravitational force or a spring force. Those are the only three forces we can assign electric potential energies to. Let's move on to the next slide. So when is the work done by a force zero? Well, there are three variables here, F, D, and let's consider cosine theta as one variable. So if any of these three is zero, then work is zero. Work is zero if F is zero, which means that there's no force. Force is really important for work. It's the force that's doing the work. So when D equals zero, yeah, that means that you're applying a force, but the object is not displaced. Common example is you're familiar with, you're pushing a wall. You're pushing a wall, you're exerting a lot of force, a lot of effort. You're applying, I don't know, even if you apply 1,000 newtons of force, but you can't push, you can't make the wall move, then you're not doing any work. So when cosine phi equals zero, cosine phi equals zero if theta is 90 degrees, or the short angle between F and D is 90 degrees. Let's see how that looks. Maybe you're moving to the right, or you're pushing an object and causing that object to be displaced to the right, but actually you're pushing upwards. I'm sorry. I need water. Is that even possible? You're pushing upwards on an object, but the object's moving to the right? That's what this waiter is doing. You see, the waiter is uh, applying a force to the upward direction, but that force is not really causing the object to move. It's just supporting the object so that it doesn't fall. As the waiter moves to the left, the angle between F and D, the short angle phi, is 90 degrees. And so that force is not doing any work on the tray that the waiter is carrying, whatever food that is. So when is the work done by a force positive? Well, F and D are, as I mentioned, always positive since they are magnitudes, but cosine phi is positive if, like, what values of cosine theta are positive. Yeah, that's when theta is between 0 and 90. When is the work done by a force negative? Well, cosine theta is negative if the short angle is between 90 and 180. So if I draw that, maybe, oh wait, maybe your your object you're pushing is to the left, but your force is to the right. Is that even possible? Or force is upward, but displacement is downward. That's the short angle for that is also 180. Is 180, and so that is negative work. Where the force is downward like gravity, but the displacement is upward. Those are examples of negative work. Calculate the minimum work. Let's look at this example. Calculate the minimum work done in lifting the 2 kilogram ball a distance of 5 meters upward. So there's a ball. Oops. Have a ball. So the ball is, it has a mass of 2 kilograms. And they say calculate the minimum work done in lifting the ball distance of 5 meters. Right. So we're trying to lift this ball. 5 meters is really high. Maybe you have long arms. Slenderman arms. So let's look at the formula. What we do know is that our displacement is upwards. And also we have to apply an upward force. So that means that the angle between our force and displacement has to be 0 degrees. And so cosine phi becomes cosine 0 or 1. So actually this part right here, if you check your calculator, make sure your calculator is in degrees. That's equal to cosine 0 is equal to 1. So actually the formula simplifies to F times D. We know that the magnitude of our displacement is 5, so that's good. But what is the force that we need? What value of force? Well, I will say that the minimum force that we need to lift this ball, we have to match the weight of the ball because the weight is just a force. Weight is mg, right? I hope you remember that. Weight is mass times 9.8. If we can match that with a force also equal to mg, since we have to balance it out, that means we can lift the ball. But since the force and the weight are the same magnitude, same value, that ball will reach what is called dynamic equilibrium, which means that the ball will move but at a constant velocity. The velocity is constant. It will not accelerate upwards, but if you want it to accelerate upwards, the force that you exert must be greater than the weight. But if you just want to lift it at a constant velocity, which is good enough, right, to lift the object, then you just have to match W with your F with W. So what we're actually really doing here is, oops, sorry again. Oops. We are doing our force has to be mg. And if we just change that D to H, doesn't that look like the formula mgh? That's how we derive the formula. So let's just solve, calculate the work done. That's the mass is 2 kilograms, 9.8 meters per second squared, and D is 5 meters. 5 times 2, 10, 10 times 98, 98, 98 joules. So 98 joules, we lift the ball upwards and we spend 98 joules. And I hope you remember what I said in the previous video. So whatever, how much work you put in to the system, that's that will change. That's equivalent to the change in the potential energy of the system. So if we have for when the ball was in the ground, if we say that the potential energy of that ball earth system 0 joules, then we apply work and the ball is now in a different location, and now the ball earth system has a change in orientation, and it now has a new potential energy as well of 98 joules. So I'm going to end here, and so thank you.